Okay, so before I move on, observations about states of matter. Avery, tell me one observation about a state of matter.
The particles of gas can spread out when liquids and solids.
Okay, so there's a difference in spacing. So solids are the closest and most compressed, versus liquids have some flow to them. They have some space between them, and gases are the most widely spread out. So which of the states of matter, solid, liquid, or gas, do you think pressure can impact the most? Like changes in pressure? Gas, because they're compressible, and so a solid's not compressible. So there's some notes that some of this is common sense, some of it's based off like just how you've experienced everyday life. Describe the shape of a phase diagram. So Bradley, what is a phase diagram and how is it shaped?
It's like a curve,
Mm-hmm.
and there's pressure and temperature on the y-x axis.
So it's like a curve, like how? Give me a little air drawing.
It's like this.
Uh-huh. There's just one line?
Well, there's one in that triple point. There's one that goes up straight up.
Okay, and the straight up line could be different versus like, water, carbon dioxide, nitrogen. It could differ. Right? But this is one part of it, and that's kind of the other part. So the slope of this line will differ, but regardless, you said the axes were
Pressure,
and
temperature.
temperature. So you should be able to realize that this is just us changing pressure on the y-axis and changing temperature. And as I change the pressure, let's say I have basically no pressure, and I have a gas, right? What if I increase the pressure on that gas? What could I possibly do to it? Compress it so much, it solidifies. It liquefies and then solidifies. So actually, by changing pressure, I can change the phase, and phase does mean phase or state of matter. So changing the pressure at a particular temperature could change the phases, but that means you know where these phases are in this image. So, Sophie, what is this one right here labeled? Look back at your paper. Solid, and then this one will be liquid, and then this one over here will be gas. Okay, so all three states of matter. Plasma is not represented on here because of the nature of plasma being electrified, and this doesn't have anything with energy necessarily on it. But temperature is a form of energy. This is usually in degrees Celsius. So what I could say is that normal 1 atmosphere, and we call normal 1 atmosphere because that's generally what we call like the location in which we live. Now, if I was under the ocean, it'd be a different pressure. If I was up on the Mount Kilimanjaro, it'd be a different pressure. But normal atmospheric pressure is called 1 atmosphere. And what I can do is I can look across 1 atmosphere, and I can look and see when phase changes occur. So solid to liquid, liquid to gas, or vice versa, liquid or gas to liquid, or liquid to solid. Those are called phase changes. So what's this phase change called when I go from solid to liquid? Say again? Somebody just said it. Say again? Melting. Going from solid to liquid is definitely melting. Okay? And so what I could do is I could actually see the point at which it melts by looking at the temperature that's associated with that point in time. The point in time is right here, though. It's talking about where the solid transitions to liquid, melts, which would be us looking here. Let's just call that 0 degrees Celsius. And so I can look at a phase change on the diagram and look at the temperature at which that occurs. Same story, different one. What is it called when we go from liquid to gas? Boiling. And so I can look on the axes here. It's kind of straight. And let's say boiling occurred at 100. So liquid to gas is boiling. There's another way to say boiling. Evaporation. They're not exactly the same, but vaporization, those all kind of relate to each other. But if that's at 100 degrees and melting's at 0 degrees, what substance am I talking about here? What substance do you know that boils at 100 and melts at 0? Liquid water, or H2O. So, and this would be different for carbon dioxide versus for nitrogen, or different for nitrogen. It's different everywhere. So the point at which all phases are in equilibrium is where?
Triple point.
The triple point. And the triple point is right here. It's where the solid, liquid, and gas coexist together. And so we normally don't isolate that very often because it has to be the perfect pressure and the perfect temperature to do that. Is this pressure lower or higher than one atmosphere? Lower than 1 atmosphere. And where would I experience a pressure of lower than 1 atmosphere? Where in the world? A mountain. Because on a mountaintop, you have, okay, so here's us. Here's beneath the sea. And here's us on top of the mountain. Okay. So here at normal atmospheric pressure, that's 1 atmosphere. And what's causing that atmosphere of that 1 atmosphere of pressure? It's not a trick question.
The atmosphere.
The atmosphere, okay, all the gases in the atmosphere. So the atmospheric pressure, which we call 1 atm, can also be written as 760 millimeters of mercury, 760 torr, 101.3 kilopascals. You remember some of those from your reading guide? So there's all these different units, just like I can say 1 foot, but it also means 12 inches. These things are unit conversions. But when I say 1 atmosphere, that means I have enough particles hit me in the head to cause 1 atmosphere of pressure. So when I'm up here on the mountaintop, what do you notice? Less particles. Less particles cause less pressure. And so if I'm at less pressure, let's call it like 0.1. I'm not sure what it would be exactly. That's a significant, like yes, a really tall mountain if it's 0.1 atmospheres. But that's lesser pressure because there's less gas particles above me popping in the head. Okay, so what if I'm down here like a snorkeler or a scuba diver? What's above me? A lot of atmosphere plus water. So what would you anticipate the pressure would be on top of me?
0. 2.
Maybe, so it's got to be more than 1 atmosphere, right? So it could be 2 atmospheres, it could be 1.5 atmospheres, whatever it is, it's got to be more than 1 atmosphere, because this right here is considered 1, and I'm below that. So there's more stuff, more particles putting pressure on them. So you can see how I can give you a scenario in real life, and you could read a diagram to actually figure out like what temperature would something boil or melt or something like that. So have you guys ever seen on the back of a nutrition label or on the back of a package like cake, making cake? It's like, if you're above this altitude, you should be using this temperature. Maybe? Okay, I'll show you a picture of that later. Never mind. Hold off on that thought. All right, last thought, because there's a lot of diagrams in this unit, and so I really want to make sure you're very comfortable with what these diagrams are supposed to be telling you. And in terms of what they're called, this is called a phase diagram because it represents phases and phase changes. And then what about a heat curve? Heat curve. It's a little bit of a lie. Is it a curve? No. Okay, so a heat curve looks like what, William? It's like a staircase?
Yeah.
Heat staircase is what I would rather call it, but we can't call it that. Okay, so it's like this.
Yeah, it's like a flat.
Okay, so what are the axes?
It's the y-axis is temperature, and then the x-axis is time.
Yeah, it's either time, sometimes it's called heat added, or energy added. It'll vary based on the textbook or diagram you're looking at, but this is always temperature. So notice what flipped. Temperature is on the bottom, temperature is on the side, right? So x-axis, y-axis. So that's why sometimes we get mixed up with our diagrams. So this is actually showing us heat being added, so energy being added, and as time occurs, or as time goes on, and we're adding energy, what are we naturally doing to the states of matter? Changing them. So we're going from what here? Solid to liquid to gas. So what are these plateaus representing? The actual change of phase. So this first one, just call that 1 and 2. Number 1 is what state change? Melting. And so just like you said earlier, melting is from liquid or solid to liquid, and 2, boiling or vaporization is the fancy word for that. So they both can represent similar things, except this one includes pressure, because when you change pressure, you will change the temperature at which that phase change occurs, whereas this one's assuming we're at the same pressure the entire time. So we're assuming, let's just say 1 atmosphere for our sake, and then we could look at the temperature at which each of these occur. Now, this right here actually has another value associated with it, and it's called delta H. We've learned about delta H. What does delta H refer to? It wasn't delta S. Delta S was entropy, which is amount of disorder. Enthalpy. Okay. And this is called enthalpy of fusion. If I can spell fusion. Enthalpy of fusion is actually the term we use for melting. Enthalpy of fusion doesn't kind of just sound like something's melting, fusing together. And then enthalpy of vaporization goes with vaporization. Good job, guys. Okay, so those are going to be some terms that we start to throw in these diagrams, and we'll do that in a little bit. I did give you guys this, so we're going to quickly fill out the table with information. I have it on the next slide. Then we'll actually hit these with some more application questions, and I think it'll be good to start the back. Okay, so it's a little short today because I'd like to wrap up state changes and faces of matter, kind of that information today. We're going to share our PBLs at the end, so I'll have you guys talk in your groups after we finish this up. So, all right, so I'll give you the first two columns. We'll talk on these. So some of the descriptions of particles and arrangement within them and motion, some of that is commonsensical because you've watched your videos, you've seen the little diagrams, you've seen how they move with each other. They've all been represented as like hard spheres or just spheres in general. So some of the key words I would think that we pulled out. Well, give me, let me ask you guys. Sophie, what's a key word from solid, anything between particles in motion? Some key words you see. So no motion. I'm actually gonna go back. No motion except for the teeny tiny subatomic particles inside that are actually moving. We know that from the Bohr model. They kind of supposedly go in an orbit or in an orbital, but basically it's motionless except for the tiny vibrations that exist. And they're packed. Tightly packed would be a good word for that. And they do have a definite shape and volume. So just like our calculator, definite shape and volume. There's no like squishing it anymore. It's already there. It's already basically compressed as much as you can. Bradley, what's a key word you see about liquid?
Particles can move around each other.
Okay, so they can move around each other, they can flow around each other just a little bit here and there. And then what about their structure?
They don't have a structure.
No, but they do have a
Volume.
So no set structure, so no shape. Yes, they have a particular volume. We can't really compress a liquid too much, so we're going to get onto gases in a second. All right, so look here where it says effects of pressure and temperature. As you can imagine, when particles are tightly packed, they cannot compress much at all. So if I increase the pressure, what does that do to the volume of my solid? Can it compress it a whole lot? No, it's basically about as compressed as it can get. The particles are as close as they're going to get to each other. Maybe just a hair more, but is it a noticeable change in volume? Probably not. So I'm just going to put volume change with a no on it. Are you getting my symbols? Okay, so increased pressure doesn't really do much for volume changes in a solid because it's about as compressed as it can get. Now, increase in temperature eventually will do what to a solid? Eventually melt it, but it's kind of duh, like we know that. So that's when we're really hitting the pressure side right here. All right, so liquid, increasing pressure. Now a little bit further apart. I'm kind of drawing a liquid here, and they're flowing. Okay, so they're a little farther apart. So what do you think about a change in pressure? What could it do? Maybe slightly, but not really all that noticeable, slightly change the volume. But just the slightest amount. Slightly change volume by just a hair. Not noticeable really at all still, because the particles are still really close together. Well, then, oh, and this is take the shape of their container. I said no shape for volume of no shape for a liquid. Unless it's in a container, then it's pretty well constricted by the barriers of the container what the shape would be. In itself, though, it's just flowing. All right, so gas loosely held, we know that. They're bouncing off the walls, they're everywhere. And so if you notice the constant random motions, it's because they have a high, this is information that's extra, and it's kind of related to over here what the red typing says, but they have high kinetic energy, KE. What is kinetic energy? Mikado, what's kinetic energy?
It's like the energy you make when you move around.
Okay, so energy of motion. So we're just redefining that once again, and this was on your reading guide 13, which you should have back in front of you as well. So yeah, high kinetic energy, and it has a high amount of motion. Well, you'll notice the rest of them, I don't really mention a whole lot of motion, so they don't really have a high kinetic energy. So now because of this, they're spaced out, right? So this guy's way over here, and I can do that across the board. So what do you think is going to happen when I increase the pressure? Say again? The volume will certainly decrease volume a lot. And so this is a significant change. It's the first significant change in volume we've seen. All the other ones are just either not at all or very minor. So if you increase the pressure, okay, I didn't tell you guys to bring this today. I hope you brought it. Did you bring your box of air?
Yeah, sure.
I forgot to tell you. Everybody whip it out. Box of air. Okay, particles are far apart. I'm so glad you guys brought it. Such good students. And then compress your box of air. Ooh, compress it, Mikado. Let's go. Okay, what happened to the volume? It's tiny. So lots of pressure, little volume. So what would you say? That's a direct or an indirect relationship?
Direct.
You guys know what direct means?
Wait.
If I increase the pressure, it increases the volume.
Oh.
Decreases the pressure, decreases the volume.
Oh.
So indirect, those are opposite, right? Increasing force of pressure decreases the volume. That's an indirect. What's another way of saying indirect? Inverse, right? I'll use inverse, and I'll also use indirect. So just make sure you're familiar with that. That's an indirect relationship or an inverse relationship. So with that information, we actually can do calculations with it, which we'll do tomorrow with gas laws. But there was somebody's name that was associated with that. You took notes on that in the last video. Say again? Boyle's law. And so because we saw this relationship with gases, but not really with solids and liquids, a lot of people started investigating gases because they acted so differently than many other particles. They had some interesting characteristics. They also were very predictable in their changes, so hence increasing pressure decreases volume. So we actually associated Boyle's the guy who discovered it. We put his name with the law. We called it P1V1 equals P2V2, but he basically explored the relationship between pressure and volume of gas quite a bit. Okay, so because I know you remember a little bit about intermolecular forces, weaker forces of attraction as you go from solid to liquid to gas. Is that news? Not really. High forces of attraction keeps them really well stuck together. Medium forces of attraction allow them to flow, and then basically no attractions, or we assume there's no attractions, or very, very little, mean that they can stay very far apart from each other. So not really well attracted at all. So a lot of common sense here, right? Or at least we're getting to the point where it's now common sense. All right. Yeah, let's keep going here. If you're in the back, please finish in the next minute, wherever you are, and then come back up here and join us. Okay, so we talked about the states of matter and how do we get from one point to another, to point A to point B. But we're just going to make sure we can associate, like when the energy goes in, we'll call it a process that requires energy, a delta H that's positive. What do we call that? And enthalpy is what delta H stands for. It's on the board. endothermic. And if we go in the opposite direction, it's not endothermic, it's exothermic. So I'm going to let you guys write down what you need to here first, and then I'll explain. Because some of these changes in state is, again, very commonsensical, but I want to make sure you have a couple notes to reference. Here in the back, please come up here and join us. So some of these are those like always true, never true, sometimes true based questions. And one of the things that you should know is that basically I can make any state occur, solid, liquid, or gas. I can make any of them occur at the right pressure and the right temperature. So because we reference both of those often, we must consider how energy plays a role in this as well. So there's a lot of variables that come into play. And as you saw in your reading guide 14, yeah, there's pressure, there's temperature, there's volume, there's number of particles. There's a lot of variables that start to come into view. But right here, we're just talking about temperature. We're just talking about energy. So at this point, we're just assuming pressure conditions are constant, so we can make these kind of hone in on the effects of energy. So we're not looking at 15 variables at the same time, because you can imagine that's pretty hard. So at the physical state of solid, anytime I go from solid to liquid, we know that's called melting. We know that for a fact. We've seen this like in 3rd grade. But if I ask you to assign a kinetic energy value to each of the states of matter, who would have the lowest kinetic energy? Who? Well, no, which state of matter? Solid, liquid, or gas? So solid, liquid, and gas. Solids have the lowest kinetic energy, and who is the highest? Gas. Okay, so anytime you're ever concerned, like, ooh, is this endothermic or exothermic? Because many times you guys like to confuse yourself. I always just label it. Okay, low kinetic energy, medium kinetic energy. Sorry, because this is liquid. So how in the world do I get from a low kinetic energy state to a medium kinetic energy state? What do I have to do to that thing? Well, I have to gain kinetic energy. So I'm basically saying I'm adding kinetic energy to this. I'm adding kinetic energy to the solid to make it go liquid, which we know is melting, but if I add kinetic energy during this process, adding is which process? Or is which style of thermal energy? Endothermic, right? Positive delta H is adding energy. So this delta H associated with that is a positive value. Now with the inverse of that, you can assume, but I'm going to make sure you're cool with not just assuming, you actually understand. Liquid versus solid, this one we'd label what kinetic energy? Medium kinetic energy. And we're transitioning to solid, which is low kinetic energy. So, oh no, I'm going from medium to low. What happened in between that? We lost or subtracted, we removed energy. So I'm going to actually put remove, that's probably the best word. Remove kinetic energy. So the word remove is associated with endo or exo? Exo, and that's showing us as a subtraction or a loss of energy. So if you remove kinetic energy to get from a liquid to a solid, your delta H is negative. So do you see how we're pulling some thermochemistry enthalpy into our associations with the phase change? It's just looking at kinetic energy differences. That's it. So this bottom part down here is what I was speaking of from warm-up. The delta H value, delta H itself just means enthalpy. And so if I say enthalpy, it's really generic. It's not very specific to what we're speaking of. So we actually have little titles that go along with them. Enthalpy of blank. So if I'm melting something, I call it enthalpy of fusion, fuzz. Delta H fuzz. So this up here is delta H fuzz, or fusion. And that's a positive value because of the whole transition point that we just spoke of. So, do you notice that 1 and 2 are simply opposites? Okay, so let's say delta H fuzz, let me write this a little bit neater up here. Let's call it a positive 100 kilojoules. I'm just going to put a number with it. If these are directly opposites, what do you think this delta H value is? Yeah, it's a negative 100 kilojoules because the energy put into this system was released from this system because they're just blatantly obvious opposites of each other. So this one's called delta H fuzz or fusion. This one doesn't have a name, but we like to try to assign it a name. It's called delta H of what process would you call going from liquid to gas or to solid? First one's melting, we call it fusion. Freezing, it's called delta H freeze. We didn't get creative on that one. And so that's the energy that's released during the freezing process. So think about that. Ice gets cold when it freezes, right? Why does it get cold? Well, but that's the definition of cold. Okay, so what happened when it went from liquid to solid? No, absorbing energy would make it melt. So why is ice cold? So isn't that weird? When it freezes, it releases energy. So if you put your hand around some liquid as it was freezing, you would feel warmth coming off of it while it was freezing. See what I'm saying? It's kind of like a weird relationship, but that's what's happening on the molecular or the atomic level. And we've done this before in my AP Chem class. We actually did evaporation. And so evaporation, which goes from what to what? Liquid to gas. You tell me, liquid to gas, endothermic or exothermic? Endo, because we're going from a medium kinetic energy to a high kinetic energy. Okay, so you're saying that delta H is, well, that's just what you said is positive, right? Because you said it was endo, right? Okay, so if I have my hand around some liquid, and that liquid is turning to gas, what would I feel? Stan? Why would I feel cold? Right, and where do you think that energy maybe is coming from? You, possibly that your hands are warm, and so if your hands are surrounding the liquid as it's turning to gas, it's sucking in energy, it's absorbing it, and so you feel a lack of energy, which is cold. So we'll get into thermochemistry a lot more, but let's keep going. Okay, so the rest of this is a lot of somewhat similar explanations, so work with me here quickly. As we go from liquid to gas versus gas to liquid, we have two different names for those. So liquid to gas we call vaporization, which is another name for evaporation or boiling. And gas to liquid we call condensation. 2 thumbs up, easy peasy. All right, so we're going from, label this with kinetic energy. Let's do this one. Gas is high kinetic energy, and liquid is medium kinetic energy. Delta H is loud and proud. Why negative? Yeah, you have a loss of energy as you transition between high kinetic energy to low energy, and so that high to low says I'm losing energy, so we're going to call this a negative value. And this is delta H, which is enthalpy of condensation. We do have little titles that we try to keep assigning them. It makes it very clear what we're talking about. And so that means that if this was negative 200 kilojoules, what would this process be? Positive 200 kilojoules, because it's the direct opposite of this process. And that's just you seeing that X is the same compound. It would be different for different compounds that are melting, evaporating, condensing, and so forth. Now, so we can try to use the terms correct with the word evaporation and boiling. Many times I'll let you guys use them interchangeably just because it's not incredibly important point. But in terms of like what is evaporation, we actually talk about evaporation occurring at the surface of a liquid versus boiling, which when you put something on a stove, let's say you put a pot of water on the stove, where does it start boiling? At the bottom. Why? It's because you're heating it, right? Okay, so that's I think that's obvious now, but if you've ever used them interchangeably, you're like, oh, I didn't think about that. So if I just have an ocean, let's just call this the ocean. Is the ocean going to boil? Hopefully not, unless the core of the Earth gets like 10 times more hot than it already is. But it's not going to boil. But what will happen to the ocean? Yeah, it'll evaporate. Little water will come out here, form water vapor, and then as it gets cold, it'll condense back. And so that's the water cycle, right? So that's evaporation. It's happening at the surface. The stuff down here, why can't this little water molecule evaporate? Well, maybe the sun penetrates the ocean a couple feet. This is simpler than you think. It's too what? Why can't this guy turn to gas? There's stuff above it. It can't get out of the ocean, right? It's actually covered up and submerged. Now, only this, because it's at the surface, can it pop out and turn to vapor. But this is like too far down in the water to be able to vaporize itself. You might see little bubbles forming at the top of the water, but that's about it. All right, and then boiling. That's what I was going for earlier. I got my Bunsen burner underneath here. Where does boiling begin? Bottom, because I'm heating it up, and then as I heat it up, it starts to boil out. So it's different than evaporation. Just making sure you're an informed citizen, that's all. Okay, oh, and then, so this was called delta H condensation, this is called delta H vaporization. All of the other delta H's, enthalpies of blank, they're all really just the state change name, except for which one? Melting, we didn't call delta H melting, we called it fusion, it's just another name for melting, but everything else is named exactly the same as the phase change itself is. Okay, so, you know what? I'm gonna hold off on this for a second. All right, so this was our phase change, or our phase diagram that we're speaking from warm-up. And those of you who are up here, we talked about what the 1 atmosphere referred to. What is 1 atmosphere? What do we call it? Normal. We call that normal. So this is normal pressure, 1 atmosphere, just because we're dealing with what we would normally experience here in North Carolina. If we're in Colorado or Louisiana, it would be different, but we do refer to 1 as normal. It's kind of our standard that we do as a comparison. Okay, so we can read a lot from phase diagram, but we'll specifically will be referencing normal often. Oh, let me finish these phase changes before I move on. So examples of sublimation and deposition. You guys learned what those terms were. These are some examples of those right here. So we're going from solid to gas. We're skipping what? Liquid. But we're still going from a low kinetic energy to a high kinetic energy. So this overall is delta H positive. And that's called enthalpy of, what process is that? Sublimation. That's called enthalpy of sublimation. We'll just put sub down there. And what's a good example of something subliming? Anybody? Dry ice. What's dry ice made of? Anybody? Carbon dioxide. Yeah, sublimation is CO2 solid going to CO2 gas. And Harris Teeter did not have it this morning, but I will get some from the other Harris Teeter tomorrow for you. Huh? Yeah, they have dry ice. You can buy it. Yeah, it's in the Penguin thing up by the front, by the red shoes. So they randomly ran out. I was like, well, great. So I was going to give you guys some sublimation action here this morning, but we'll do that tomorrow. So sublimation is going straight from gas, solid to gas, and dry ice is a good example of that. Now, deposition is the opposite of that. So we're going from gas to solid. Anybody have a good example of deposition? Gas to solid, no liquid. You guys see the frost warning, freeze warning over the weekend? No, you guys don't watch the news? Okay. So, was it not on Twitter? I'm sorry. Okay, so freeze warning or frost warnings actually are examples of this because they actually go from straight gaseous or water vapor and then they deposit it like on plants, on especially farmers. They need to be aware of that because that's frost, which you've seen dew and frost
on your grass or on other plants around. Dew is more of a liquid, so I wouldn't consider that deposition. But like a freezing warning would be going straight from water vapor to solid on your plants, and that would kill your plants, and then you'd have to figure out what to do for your living at that point. So sometimes that's important in industry. And then another example, and you guys tell me where this falls. You guys know those like air fresheners that are you put in your car, you put in your little well, the trees could work, but also in your air vents. Okay, okay, and those little things. What would you consider? Because then you start to smell it pretty soon, right? What would you consider that to be? Is it a liquid? I'm thinking about those little solid sticks that you can stick into the. That's sublimation, right? Sublimation, so you have a solid and it goes directly to vapor. Well, how do I know there's no liquid? Because you're not feeling like wet air freshener pop on your face, right? So you smell it eventually, and you're like, that smells great. And that's because the gas is going into your nose and says, hey, nose, you're smelling flowers, or you're smelling pine tree. And so that's true. You know those little cone air fresheners they have in your home, like the resonance? They're like you pop the top off. Okay, that's solid going straight to gas. Okay, so that's enough of phase changes in general. Let me give you a quick break, and you guys can sing this along with me. Oh wait, oh there's more. No, that's not it. You have to watch the lyrics. You know the song? It's called The Four States of Matter. You know the song?
It starts with solids. I do know why. Can't change it no matter how we try. Definitely shape the volume is locked in particles in position. Liquid and fluid thing. Particles slide by as the pendulum swings. Watch them in the glass, so we're thinking it shape. Volume stays the same. Gaskets, unreal. Moving particles. Watch them move out and into and fro. Trying to hold shape, but can't do it, no. Volume can change. Then
there's more. Numerous informative stanzas.
Solid to liquid, absorbing energy atoms and the thermal chain. Freezing is the way energy removed from liquid to solid. Big polarization. Liquid to gas happens in boiling. Second form is always evaporation. Remembering all boiling point changes atmospheric pressure. Condensation. Shapes are the way they were before. Changing gas to liquid atoms together more. Energy is removed so in motion down exothermic the chain oscillation. Changing solid to gas molecules tightly packed. I won't spread apart. How it's meant to be. Added energy spreading like a tree and the third chain.
Come on, guys, this is good. I'm feeling it. Oh, there's more. They took some time with this. I've watched this a number of times. Alright, I'm going to stop after this is getting screamy. Alright, so, you feel me? You knew that was good. This person, temperature change. That's the screaming part. That's my favorite part. Okay, so now we're going to actual phase change with the phase diagram. And I think I can do this from the back, actually from the worksheet that is here. It's a little hard to see. Can you guys see that okay? It's dark. There should be one at the desk. Everybody has this? Okay, so you know your states, you know which is solid, liquid, gas, you know where the triple point is. Label what you need to. If you can't see the end, I'll make it bigger. What's in line? Hi. Right, yeah. S3. Robeson Harris. Yeah, I don't think it's caught in Title I. She didn't leave when she was on holiday. Oh, and Justice Mississippi County. Thanks. Bye. Okay, got sorry about that. So, the only part that we didn't speak of during warm-up was the fact that you can change one atmosphere to a different unit. And so, what do you think 101.3 is? Right, 1 atmosphere, which equals 101.3 kilopascals, which you learned about in Reading Guide 14, is another way we could depict the axes here, but it's definitely always pressure versus temperature. All right, so from here, I'm actually going to do the questions on the next slide because you guys have your diagram right here. So these right here are all regarding this graph. That's really hard to see, okay? But you can see the labels A, where's B? At the triple point. So B is down here at the triple point. If you can't see it, it's like a little cut off in your diagram. C is up here, and D is over here, okay? I think that's everything that's labeled. Yep. All right, so let's look at these questions, and they are mostly right next to your graph. What does the segment B to C represent? Raise your hand when you're ready. That's the interface between what two phases, Kaylin?
Solid and gas.
B to C.
Oh, wait.
So we're looking at the graph here. Like this, right? Solid to liquid to gas. Where's B?
It's like in between.
Right here, the triple point. This is B. Where's C? Up here? So that's the interface between what two phases? This right here. Solid and liquid. Okay, so everybody, what's the phase change between solid to liquid? Solid to liquid. Melting. Okay, what about liquid to solid? Freezing. Okay, so we're going to call that a really weird way of saying it first, but the equilibrium between solid and liquid, but really that equilibrium word just means that they're in constant motion from solid to liquid or liquid to solid. It just means that they can continually go back and forth. But we could also say that's every single point at which that substance melts, or every single point at which it freezes, because it doesn't. We don't know which way we're going with it, left to right or right to left. So I'm going to put MP for melting point and FP for freezing point, because it's different across the board there, but it is different based on pressure. Okay, so using that same logic, what is A to D representing? Where's A? Down here at the bottom. So what's A to B representing? Sublimation and deposition. Good. So equilibrium between solid and gas, and so that's going to be every sublimation point and deposition point present within that compound. Of course, it's at different pressures and different temperatures, but that's why we're not specifying the point actually. All right, B to D. Right, so from B all the way to D, which is up here, is equilibrium between what? Liquid and gas. And that double-headed arrow just means it can go, you can think about it either way, liquid to gas or gas to liquid. And what would that point be? Vaporization point or boiling point, and I heard it condensation point. So my abbreviations are just referring to the phase changes there. All right, so what's the pressure at the normal boiling point? Everybody can tell me that right now. Pressure is what? 101.3 kilopascals, aka 1 atmosphere. And why is that point significant? Say again? Say that one more time, sorry. Everything is normal. I'm gonna modify that a little bit and say this is the pressure at which we live, and so at that point, that's what we're specifically referencing, because it's more realistic to us as to what point does that particle boil or freeze or whatnot. Okay, so here's the interesting thing. Every single phase diagram is particular to a specific compound. So I'm going to go forward and show you one example of that first, and we'll come back to this question. So look at this. So you see this guy's pretty straight up right here between the solid and liquid. But what do you notice about over there? Slightly what kind of slope? Slightly negative slope. This one almost has a slightly positive slope. So what makes that different is, one, what compound are we talking about? You'll notice this one over here is for, what's the one on the left for? CO2, you see it right here? And water's on the right. So CO2 is over here, water's over here. Well, those are two very different compounds, very different. Before I even tell you about the axes, or about the little slants here, what do you notice over here with CO2? When does it boil? At 1 atmosphere. Where does, sorry, let me go. Where's this normal boiling point? Normal means what again? Where's 1 atmosphere? Okay, where does it boil? What state changes this? So it doesn't boil. It does not have a boiling point, a normal boiling point. Because it does not boil below 1 atmosphere or at 1 atmosphere. Trick question. Okay, you have to read the graph. Solid, liquid to gas. Okay, so it doesn't start to boil until you reach what pressure? 5.2 atmosphere. Holy cow! Where's that at? I have no idea. Like beneath the ocean, may not. Well, it'll be like deep in the ocean at that point. But normally we see things like this. Oh look, water. Normal boiling point is what? Where's the normal boiling point? There's our 1 atmosphere. There's our liquid to gas change over there. So we look down, we see 373. Yeah, so 373 Kelvin is what Celsius? 100, right? Well, we know water boils at 100 degrees Celsius, so that kind of makes sense. I'm just showing you 2 different units. So you can read a lot. You can see a lot from a given diagram, especially the axes you're going to be particularly paying attention to. Okay, so this right here is the reading, but I only want you to write down like 1 or 2 things here, and then I'll be done. Okay, so what if I do like that? All right, so basically as I look at water, we know water is a solid. This is its ice form over here. What do you notice as I increase pressure? As I go from here to here to here, let's just call this 2 atmospheres, what happens to the melting point, which means the temperature at which it melts? It goes where? It gets lower. So here it's like 273.2. Up here it's like, oh gosh, 273, drop by 0.2. Up here it's probably a little less than 273. So it got lower. So increasing the pressure caused the melting point to lower. And so there must be some reasoning behind it. Water and like 1 or 2 other substances in the entire world is the only thing that gets that negative slope. Everything else, increasing pressure has a positive slope, so it increases the temperature at which it melts. Everything else, like 99% of the substances in the world will do that. Because this makes sense. Increase your pressure on anything. Ooh, squish it together, right? What is melting? What happens to the particles? They loosen up. Well, what if I'm pushing so hard on it I can't loosen it up? I'm going to have to crank that temperature up, right? I'm going to have to heat that baby really hot to get it to move, to actually go from solid to liquid, meaning melt. So if it's under high pressure, it's going to have to increase the temperature because they just naturally are so condensed together, they don't want to separate. But water, on the other hand, is weird. It has the opposite effect. So when you look down here, write down the liquid phase. Oh, hold on. Well, I'll tell you to reference the crystalline structure of water. Water is an ice form. Does what on liquid water? It floats. Do most things in their solid form float on their liquid form? Yeah, most of the time not. So anything liquid is less dense than in solid form, except for water. Water forms a what when it crystallizes? I remember drawing this when we did hydrogen bonding. Say again? You guys remember this? You remember water connected to water? 1, 2, 3. I can't remember. It's a hexagon.
Crystal.
Okay, it's an octagon. Okay, so regardless, this is water connected to water connected to water in ice form. What's in the middle? Say again? Nothing. So if nothing's in the middle, it's taking up a lot of space, but is there a lot of mass in that given space? So its density is what? Yeah, its density is low. So if density is mass over volume, decrease the mass, increase the volume, you got a low density. And so that low density makes it able to float on its liquid form, whereas nothing else can. And that's why if I compress this, I break the crystal, it melts in an instant, which is why our temperature is lower than what we initially thought out. So it's got some complexity to it, but basically just remember it's crystalline structure, low density causes things to act funny. That's it. Okay? All right, so let me pause on this. Go to on the back, it says diagram practice. Go to section 3 phase diagrams, which is the whole right-hand side. I'm gonna give you guys about 5 to 10 minutes maximum to do that. I'm trying to keep an eye on the time for us. 5 to 10 minutes. Section 3. Work with those at your table. In this case, yes. All right, pause your conversations in 5, 4, 3, 2, 1. All right, so for normal boiling point, Avery's table, what did you look at for normal? Say again?
In the back, it was 101.3, right?
On the other side, yes, it was 101.3 because that was what kilopascals was published as. So what does normal mean in general?
All of these shit, yeah.
Somebody else at your table? Right, 1 atmosphere is our normal atmospheric pressure, which is equivalent to 101.3 kilopascals. So what's the normal, where are you looking at for normal freezing point? What are you looking at for the interface? Right, and so if we label solid, liquid, gas, the interface is going to be at the 1 atmosphere mark. Mine's going to be a little bit not to scale, but when you look at your dashed line across, where does solid and liquid meet? Right here. What temperature was that published to be? Approximately 100. That's our normal freezing point or boiling point. I mean, freezing point or melting point, depending on which way you're looking at it. What about the normal boiling point, Frank's table? Why 400? That's where liquid and gas meet at the 1 atmospheric pressure, little denotation. So mine's like I said, not to scale, but right here where where the liquid and gas coexist together, that was approximately 400 degrees Celsius. You guys with me so far? Yeah? Okay. If I had a quantity of a substance at 1.25 atmosphere and a temperature of 300, and you lowered it to 0.25 atmospheres, what phase change occurred? Zach? Vaporization. So where was your point? Where was 1.25 and 300? Where does that intersect?
in the liquid region. So my little, not to scale graph's not helping, but oops, 1.25 atmosphere, 300 is about right here. So that's where the 1.25 atmosphere, 300 degrees Celsius was. And then what'd you basically look at?
1.25 and I drew a line across, drew a line down.
Down to where, at the same temperature where it existed, right? So you basically went from here to here. So you went from liquid to gas. So what phase changes liquid to gas? Vaporization. Where is the gas and liquid indistinguishable from each other? We didn't reference that this morning, but this right here is called the critical point. The critical point is where the gas and liquid basically cannot separate from each other, so we call it indistinguishable because you can't tell what state of matter is. So as I go to the as I go up on this graph, what happens to pressure? It's increasing, right? You're squishing things together, you're compressing them. Well, the liquid's like, okay, I'm compressing. But as you go this way on the graph, what's happening? Temperature is rising. So what are the particles trying to do? Well, they're trying to move faster, and as they move faster, they naturally kind of separate, right? So you're compressing it, but they're trying to separate. You're compressing it, and they're trying to separate. So that's why you can't really see, is it a liquid or is it a gas, because it's kind of coexisting together. I like to call it a liquid because it's neither, but it's both. Okay, so that's the point at which it's so high pressure and such high temperature, neither can really actually exist. Yeah.
Does that only happen for liquids and gases, or can it happen between solids and
Most of the time, the high pressure just makes it go straight to solid, if between those two, because those are so close to each other anyway, and how they look. The gas is the only one that's really far out. They're so separated. Okay. What temperature will pressure and what temperature will they coexist? Triple point. Right there, whatever that is. Okay. No.
Draw that or on your graph, like what's there. Not right now, at the end of class. Thank you. Okay.
I love interruptions in class. It's my favorite. Okay, so this is called the heat what? Heat what? It's called a heat curve. Is it a curve? No, I'd rather call it a heat staircase, but I don't have that kind of power. So if that's a heat curve, what do you think a cool curve looks like? The opposite. So like, how do I start? Okay, I'm high. Do I start with a flat line or a slant? Okay. Am I done? All right, what state is this? And this is? Okay, and what phase change is this? Say again? Condensation. This one? Freezing. How is that different over there?
the opposite?
It's the opposite, so the opposite phase change occurs. And then what else is different here? That one is a heat curve, so I'm adding heat. I'm adding heat, and as the heat is added, it's phase changing and phase changing and phase changing. The particles speed up, there's a lot of kinetic energy. So this entire graph is representing an endothermic or exothermic change. Endo, right? What clue gave that to you? Added, okay? Endothermic all the way. So this one must be representing an exothermic change all the way, because I can't just keep on holding on to my heat. If I'm a gas, I'm going to have to release heat or energy to turn liquid. And as a liquid, I have to release heat or energy to turn solid. And so releasing energy is our endothermic. So that's relating back to some of the stuff we introduced with. So on this one, I really just want to make sure you know how to read the graph. Well, the notions of MC delta T and delta H fuzz and MC delta T, that's actually more related to our maybe like 2 or 3 weeks away from where we are right now. So I want to make sure you can actually specifically tell me what's happening, and then we'll get into the calculations in like 2 weeks, okay? So on this curve, on this side, I'm going to start at section 2. You guys ready? Okay. So on section 2, first question, what is the phase at the point A? Solid. I'm going to use this as my diagram just because I don't have this diagram in front of me. So yeah, I'm at the lowest kinetic energy
and I'm a solid. How do I know I'm at the lowest kinetic energy? I'm at the bottom, but also I'm at the lowest. I'm at the lowest temperature and the lowest amount of heat added. So are temperature and heat the same thing? No, they are not. Because if not, I'd be labeling the same thing here. So lowest kinetic energy, low kinetic energy state of matter would definitely be a solid. All right, looking at what phase is substance at point F? Gas. And I'm at the, what would you say here? Highest kinetic energy. So those particles are moving up, bouncing around the fastest. You see my little diagram up here? Versus these particles are not bouncing around whatsoever. They're very, very motionless. Okay. What is the general term for the points, for what is happening from B to C? So on your graph, where's B to C? Here? And this is C, this is D, E, this is F, and this is A. All right, so what's happening from B to C, everybody? Which one? There's like 6 of them. Okay. This is, right, so it's saying from B to C, so you are referencing from solid to liquid with that respect. So yeah, that's melting. Easy. You can call it fusion if you want to be fancy. Okay? And then what about this one? I'm going to go vaporizing just in case we're not boiling, but it could be boiling too. So vaporizing, and you can see the difference here. So what do you notice here on this diagram? What 2 states of matter do you see? Solid and liquid. This is just solid and this is just liquid. So at this interface, at B I have more what? Solid, but some of it's starting to turn liquid. At C I have basically almost all. No way. Okay, we'll finish this worksheet during intervention. I'd like to finish our. Oh, well, I'll tell you guys during intervention. We'll do our PBL gallery walk. Good talking to you guys today. Bye.